The bias cap is leaking. The cathode bias cap for the first preamp stage is leaking. Wow. So a long time ago, I put a line out in here.
So when you say a long time ago, what are we talking?
70s.
Wow.
That's the only thing I ever did was I wanted to have a line out so I could use it as a preamp, or use or get a slave out and run it into another amp for more power or something. I don't even know what thought I was trying to accomplish. But what I'm going to do is I'm going to take the tubes out and I'm going to power it up. Oh, it's got Sylvania 6CA7s in. No, 6L6s. Yeah, the Sylvania 6L6s. And man, this takes me back. So this is a 12AT7 for the phase inverter. And then it's got these Amperex 6681s, which are computer grade 12AX7s. That when
computer grade.
Yeah, when 12AX7s were kind of hard to come by in the late 70s, our tube distributor was just like, "What do you got?" Well, we're all out of 12AX7s, but we have this and we have that, and variations of 12AX7s, and the Amperex Holland 6681 sounded really great.
Wow.
So of all the major brand tubes that were available, those sounded really good. So I bought up this is when I was working at Valley Arts, and I bought up a whole bunch of them, and I kept a stash for myself, and I stuck them in here.
Drum roll.
What's in here?
Filter caps.
The all original filter caps. They're starting to push out.
Yeah. Those little bubbly bits.
And these are all the downstream caps.
Do they swell before they leak?
You can tell, if you come over here, you can see they're kind of bubbling out a little bit.
Yeah, these are the pressure relief valves on each capacitor.
Oh.
So they will...
Is that a good indicator of like this one's going to go soon?
Well, they don't really go. These are the downstream ones that just act as filtering for the preamp stages. So there's not a lot of voltage or current on these three.
Yeah, you're touching them.
These two, well, it hasn't been on for...
I know, but I just see you doing that, and I'm going...
Probably 20 years.
Is that where you get electrocuted if it's plugged in?
Oh my God!
Kinda, yeah. It sort of has to be plugged in. But this is where all the high voltage is right here. And those look good. Those are the ones that I would worry about if they would short out. If they would short if they failed, and then it would blow a fuse. So what I'm going to do is I'm going to take the tubes out and I'm going to slowly power it up, because that's how when capacitors haven't been charged for a long time, you bring them up slowly.
Oh.
Bring the voltage up without worrying about the condition of the tubes.
Okay.
And then after we go through that whole process, we can measure the capacitors as we're bringing up the voltage.
But wouldn't that doesn't vary as you bring up the voltage?
It does. But what we'll see is if any capacitors are bad enough that they're going to fail under full power, we'll see a big current spike as the voltage comes up.
I see. Okay.
And if I don't get a current spike and everything comes up, and then what I'll do is I'll measure each capacitor's capacitance before we start, so we'll have a baseline.
Got it.
And I've got two different ways of measuring the capacitance. I got two different kinds of tools. A meter for that. I have a capacitance checker, and I have what's called an LCR meter. So I'll use those to check the capacitance of all the electrolytics that are in here and see how they read. And if they read okay, we'll just gradually bring up the voltage. And if they still hold their proper capacitance, then we'll check the voltage from across the output of the supplies that are going to the individual tubes once the tubes are in. And so we'll be able to tell if there's any leakage current. There'll be a voltage drop across these resistors that's higher than normal. There'll be more voltage drop than normal if these are leaking. I'm leaking current, not just leaking goo. And if they're not leaking current and they're displaying their correct capacitance value, then I'm not going to change them because I don't use it often enough to worry about if they need changing or not.
Yeah.
And if they're close enough to within spec that they work okay, then that's kind of part of what we're talking about here, is that just because they're old doesn't necessarily mean you replace them.
Sure.
And as you probably have seen with vintage amps for sale, somebody's selling something that's been recapped, but they give you the original caps with it. Mm-hmm. Like, well, what's the point of that? You're going to put them back in? I'm a proponent of, if they're good enough to work and play once in a while, like you play it once a month, once a week or something like that, and you're not gigging and it's behaving okay, or you even are gigging but you're not doing a world tour with it, right? If you're really putting it through its paces, then you want it to be up to snuff, because in an environment like that, you're going to be someplace where there are no parts, where there are no techs, and one's going to fail and it's going to start humming, or it's going to blow a fuse.
Well, that's the thing that I remember,
right,
is going through these old Fenders and, not bothering to really check them out. But then the first time I stick a mic in front of it, it starts doing the motorboating kind of thing.
Right.
I'm like, oh crap, okay.
So when you're going to be in an environment where that kind of behavior is going to start becoming apparent, that's one thing.
Uh-huh.
But sitting around the studio, and probably once I do this and get it all checked out, if everything gets sort of like a relatively clean bill of health, I'm not going to change them.
Mm-hmm.
And I'll turn it on like once a month.
Do you just have to let the power run, or do you have to play through it to get the
No, you just have to apply power. Because what happens is the electrolyte inside, it kind of separates, kind of dries out.
Is that something even with modern the last 30-year amps, you should turn them on once a month?
Oh yeah.
Oh.
It's like salad dressing. When you look at it and you haven't shaken it up,
right,
everything separates. Like, you don't want to put that on your salad without shaking it up.
So when they haven't seen voltage for a long time, you slowly apply the voltage. You bring it up very slowly, and they will recharge, and then the electrolyte inside will stabilize, and then they'll be good for some more miles. How many? We don't know, but it should be relatively good for more miles, and you'll be able to tell, is this one really on its way out? It'll show up on a meter. And that's the whole thing about just the default cap job. Oh, I got an old amp. Okay, I'm going to go get the cap job. Well,
the first thing you do, take it to your tech and have it all yanked out and replaced.
My attitude has always been, no, the first thing you do is check them to see if you can measure leakage. And if you measure excessive leakage, then yeah. And if you don't measure excessive leakage, that means the capacitors are okay. And once they've been stabilized and operational, and they're staying stable, you leave it on for a while, you have a meter sitting on it, and you can see the voltage if it's stable. And if it's staying stable, then it's going to be stable. And the amount of use that it's going to get isn't going to cause it to just like burst into flames or anything. But maybe one day I'll turn it on and I'll start playing through it and I'll hear, or like he said, you'll start motorboating or something like that. Motorboating usually happens in the downstream capacitors, the ones that go to the preamp tubes. because what happens is each capacitor is filtering it's actually not filtering so much as decoupling. What it's doing is it's preventing AC current from flowing back upstream to the previous tube stage or the next tube stage. So that's how, if you're playing through the amp and one preamp tube has signal on it and another adjacent tube has signal on it, but there's no decoupling capacitors because they're open or not doing their job, then those two stages can talk to each other. And if they're two stages that are in phase, they'll start oscillating back and forth. They'll talk to each other through the power supply lines. So what these filter capacitors are actually doing is they're preventing frequencies from bleeding from one tube plate to the other tube plate through the DC power supply lines. So they would have to be open for that to happen. The other condition is it's shorts. If it shorts, then there's no DC to that tube at all. That's easy to check. If it's drawing a lot of current, like blows the mains fuse when you turn it on, that's the filter capacitors. They're actually storing electricity in order to smooth out the ripples in the power supply. So they're the ones that are doing all the work and getting all of the current flow through them.
I'm just laughing at how little I knew when I used to do all this stuff. Because if I heard anything in there, it was like, just change them all. You got to change them all. Those are the filter caps.
And I think that's what people glom on to when they're doing the do-it-yourself thing.
And you don't know what you're doing.
You don't really know, so you default to the worst case scenario and you correct for that, which is strip out all the caps.
Well, and not really to my defense, but this is what everybody said to do.
Everybody says
that was the prescriptive measures to take.
So when we go out,
your amp makes weird noises. Change it all.
We go out in the show and don't just automatically recap an amp. So you have to ask yourself why everybody says that.
Right. Well, I didn't.
All right. So
that's why you're Steve Fryette and I'm not.
Okay, so we have the amp up on the bench. We have the tubes out. I have the Lcr meter here, digital voltmeter there, another digital voltmeter there, a scope there, signal generator there, an additional scope if I need it there, and the power station over here is acting as the load for the amp. I have my regular test load up here. It's 8 ohms, 100 watts that I use just for regular, normal stuff. Where I don't really care what the load is, I'm just getting a reference. In this particular case, we're trying to extract a bunch of different data. So I'm using the power station as the load for the amp for a couple reasons. One, because it'll switch to 4 ohms, which is what the impedance of the concert amp is, going into 4 8-ohm 10s. So it's 2 ohms. Which this also has a 2 ohm setting. And
Swiss Army knife, I tell you.
And it's got the reactive low switches. So when we're checking it and we want to see that it behaves like an amp plugged into a speaker, we can set it into reactive mode and get that behavior.
Wonderful.
All right, so we can observe all that. The Lcr meter and the digital voltmeter, I'm using them both in capacitor test mode. The Lcr meter is a dedicated piece of test equipment for measuring inductance, capacitance, and resistance. Inductance, the symbol for inductance is L, thus LCR, inductance, capacitance, resistance. So it will automatically do whatever test you want it to do, or you can select it to do the test that you want it to do. But in this case, we're set up to check capacitance. It tests capacitance in a different way than the digital voltmeter will test capacitance. So we're going to use both pieces of equipment to check the capacitors, because we're going to be real anal about checking the capacitors. We want to know if they're good, even though they're old. These are the original capacitors throughout the entire amp, and we're going to demonstrate whether or not we need to replace them and why. And the way we're going to demonstrate that is we're going to test them first to see if they're anywhere near their rated capacitance, and then we're going to do a current test where we're going to check to see if there's any leakage under load. So we're going to start with the capacitors that are inside the chassis, and then we'll flip it over and do the capacitors that are in the power supply, which are the ones that really get the load. So starting with the Lcr meter, we've got the capacitor that's in the bias supply, which reads, which is labeled 25 mics at 50 volts. And the Lcr meter doesn't really care about polarity, so I can connect them either direction and it won't matter. And according to the Lcr meter, this is the capacitor is reading 35 mics. I should probably also include this caveat: this amplifier has not been turned on since probably 2001 or 2.
Right.
So it's been
wow.
It's
been 20 years.
It's been over 20 years since the last time we powered it up. So when we do power it up, we're going to do it carefully so that we don't damage the capacitors if they're even good. The other thing that we should talk about is capacitor tolerance. Electrolytic capacitors generally have a wide tolerance, typically in production grade capacitors in the range of 20%. So a capacitor that's rated at 25 mics and reads 35 mics on a meter, that's well within the 20% tolerance. You've got basically plus or minus 5 mics and it's 25 and it's reading 35. That's probably 22% plus on the plus side, and that will be fine. Now, just for giggles, we're going to put the capacitor tester mode of the digital voltmeter across the same capacitor, and we're going to get 66 mics. Now, why would we get 66 mics? It very well could be, besides the fact that they check things differently, it also could be that the digital voltmeter doesn't do as good of a job of testing the capacitors in circuit as the Lcr meter does.
Okay.
So that doesn't mean that this meter is telling me the capacitor is relatively good and that one's telling me it's relatively bad, because it's actually saying that it's got 2 times the capacitance, a little more than 2 times, 2.5 times the capacitance that it's rated at, which actually is not a bad thing, it's a good thing. But again, we're testing it in circuit, and that could have a bearing on the reading that we're getting. If I reverse the polarity on the digital voltmeter, as you can see, we don't get anything. The digital voltmeter is passing a very small voltage through the capacitor to generate that to calculate the capacitance value. The Lcr meter is also doing that, but it's doing it in a slightly different way. So, like I said, it doesn't necessarily have a polarity, and we're going to test that theory by reversing the leads on that capacitor that was reading 35 mics with this meter, and we get 35, the same 35 0.25 mics that we were getting with the probes wired the opposite direction. So this is giving us a more accurate in-circuit assessment of what the capacitors are doing. Now we have another one. This is a cathode bias cap in, not sure what stage this is. This could be that's the phase inverter. So this is going to be the tremolo tube. And this is the first 2 gain stages for the normal channel. This one's the first 2 gain stages for the vibrato channel. The next one is the tremolo circuit itself, and the next one is the phase inverter, so that's not too difficult to just eyeball and figure out. Okay, so we're going to the bypass capacitor of the tremolo circuit, and we're getting 31 mic on the Lcr meter in circuit. Now I say in circuit, but I've taken the tubes out, so that side of the capacitor is not going anywhere except the pin of the socket. It's not going to the tube, and it wouldn't matter if it did have a tube in it because the power's off, so there's no current being drawn. However, it does have a resistor in parallel with that capacitor, so when we go and do the same test with my digital voltmeter, we get, again, about a 50% higher rating.
Interesting.
And that's going to be because the resistor, it's not adequately zeroing out the resistance that this capacitor is operating in parallel with. Let's do it the opposite way. We've got these two capacitors are dual capacitors. So two capacitors in one package with a common ground on each one. And again, 25 mics, 25 volts, I believe, yes. So one side is going to the other triode of the tremolo circuit and reading 0.2 mic, which is way off. And the other side of it is reading 0.3 mic, which is also way off. Now that could be for two reasons. It could be because of the way the meter is resolving that reading, or it could be because the capacitor is bad. So we'll go and double check it with the LCR meter, and what we got there is 17 mic on one side and 17 mic on the other side. So that's, again, within tolerance, 25. So 20% is 5 mics. So this is minus 5%, actually about 6%, but still, we're getting a reading that's within tolerance. Again, these readings are being taken with no voltage applied and having not had any voltage applied for 20 years. The last capacitor that we're going to check here is also a dual. Now this one is reading 100 mic on one side. And then the other side of that one is reading 108. Same capacitor, very similar resistors across them in parallel. Why are they reading so differently? Let's go over here and see if we can get an answer to that. Go to the ground. We still have that way off number over there. This meter is not doing a good job of testing dual capacitors in a single can. So part of why that's misbehaving could be because of that, and part of it could be because they're bad. So let's look over here, and what we see is on this capacitor, this is the hot end over here.
Okay.
Let's just go look at that. If you look in this side, there's no...
It's interesting, the cardboard swivels around there.
Isn't that cute? Mm-hmm. This is the positive side,
okay,
which is the side that you would see if it was starting to try to squeeze its guts
and
out of there. It's not. This one is not trying to die. The same is true of this one. It's perfectly clean in there, and it's reading close to its tolerance, so that one appears to be good. This one also read pretty good. It was reading 17, 18 mics per side.
Right.
You can see that little black ooze right there.
Oh yeah, look at that.
That's guts coming out.
All right.
But we're still within tolerance. Now this one, you can see that there's some major goo coming out of there.
Oh, look at that.
That black tar. It is connecting between one of the hot sides of the capacitor and the can. So if that black stuff has got any conductive property to it, it could be acting as a short to the can. So this would be a suspicious capacitor.
Right. Well, it already is, right?
Yeah. However, that doesn't necessarily mean it isn't going to work. It just means that it doesn't look great. So
well, it's also reading funny, right?
It's reading funny. So just for the heck of it, I'm going to
break that bond.
I'm going to break that circuit of the goo that's in there. because I'm not ready to give up the ghost on this capacitor yet. Just out of pure stubborn
original
refusal to submit to fate. Now, okay, we got a nice chunk of that out of the way, so that if there's anything conductive in there, it's out of the circuit now. Okay, now.
And does it swivel all the way around? Like,
yeah.
Okay.
It's just a
so
covering.
If they're swelling, would it stop?
No, no,
Okay.
because the swelling you'll see coming out of the end of the.
Okay.
This is the rubberized side of the can, and you'll see that stuff coming out. Of
Okay,
the
so
inside of
the can itself won't puff out and cause that cardboard stuff to no longer.
that would only
rotate
happen
around.
under really extreme circumstances.
And it would
in
probably
this,
already be oozing like crazy out of the end.
Yeah,
anyway,
and in
right?
this part of the circuit, the voltages are so low that it won't.
Okay.
The likelihood of that happening is practically zero. All right, so now we go back here. Tell us what you got. We're still at 100 mic there.
Ooh,
It went down a little bit. We were at 120 before removal of goop. These leads can be a little sensitive, but we appear to be doing okay. I don't see anything that's making me making me feel like I absolutely have to take capacitors out yet.
So here's a question: if everything were running right now, tubes were in, and we're plugged in and we're playing, and that capacitor is bad, what would be the audible result of that in the circuit at that point? What's that doing in the amplifier?
It's bypassing AC signal to ground below a certain frequency.
Okay.
So if it's open, the actual gain of the stage would be low.
Okay.
And it would be, it wouldn't have like a frequency component per se. In other words, what these capacitors do is they bypass AC to ground below a certain frequency. So if it's open, it won't do that, which means that stage would have less gain and it would sound bassier. If it's shorted, the signal would probably die, or the gain would go low and it would get very, very thin, because a shorted capacitor is a short circuit, which would actually behave like a much higher value capacitor, which would roll off more low frequency.
I see.
So the gain would go down.
So it's going to be anemic.
The current through the tube would go up. It would probably start to sound fizzy and anemic, and the gain would be lower than it should be.
And you'd go, what the hell happened to my bottom end?
Right. And the beauty of the two stages is that they're set up pretty much the same way with regard to the signal going into the first stages. So we can actually check the bias voltage and the current flowing through each of those stages with this capacitor, which is reading sort of normal, and this one, which is reading not normal, and see how different they are.
Well, here's a question. Talking about these things interacting in particular ways and getting used to how your amp sounds. If this is shorting and it is rolling off low end.
Actually, this one is not shorting.
No, if it was.
If it was,
then
right.
if just hypothetically, if the owner of this amplifier was used to using this in a way where they crank this amp up all the time, they're like, it sounds great because it doesn't get that typical Fender low-end flub.
That's right.
And then you change that out to a functioning cap and you got that low-end restored, you might have somebody saying, what did you do to my amplifier?
And I have had that. I had people come out, hey, this thing was like golden before I brought it to you. What did you do? I did what you asked me to do. Put it back to the factory operating condition, which now we have discovered you apparently don't like.
Yeah, exactly.
And it's very difficult to have that conversation with the customer because they have to accept the fact that if they trust you and know that you know what you're doing, they have to accept the fact that what you're saying is probably true, and now they have some recalibrating in their head to do.
Sure.
Okay, so now we're going to the power supply filter capacitors.
And it always freaks me out when you touch them like that.
Well, remember, again, it's had 20 years for all the voltage to drain out.
Sure.
So there's not any likelihood. Still, I know that people that aren't really sort of electronic savvy or would never do this.
And that's me. Well, to me, it's like, dude, how are you putting your fingers on the burner while it's hot?
Yeah, well, it's because it's not hot.
Right.
But still, there's the voodoo
Totally.
of that it might be because capacitors hold voltage. Yeah, they do.
See, now I'm going to...
Right. Okay, so here we have one capacitor that's really starting to show that it's having a end-of-life crisis here
Right.
by the end bubbling out.
Yep.
So an average tech would look at that and just go, replace that. That's no good. And since we did that one, we should probably do this one because it's kind of starting to show its age too. If you look right here,
Yep, totally.
there's a slight rise there. That's going the same direction this one is. And this one, a little less of a rise, but still it's there.
Visible. Yeah.
The upside to all that is capacitors and guitar amps are operating at very, very low currents, way lower than the current, maximum current they're specified to be able to handle. Like a fraction. The ripple current on a capacitor like these is probably pushing 300 to 500 milliamps, and the actual current flow through a capacitor like this is usually 1 on a good day. So they're operating well within their safe operating range. So even when they are starting to do this leaky thing, it doesn't necessarily mean that they're not going to operate well enough to operate the amp. With the power supply capacitors, different ball game because they are operating more closer to their operating range in terms of voltage and current. We've got 350 volt capacitors here, 2 of them in series for a total of 700 volts. And so this power supply probably has something in the range of between 450 and 500 volts on the two. So there's 200 volts of extra margin of error on these capacitors. So you'll see that there's no stuff getting forced out of the guts on either one of these. So these are the capacitors that normally will go first. And as you can see by looking at them, they physically look good. So now, let's see what the digital voltmeter says. And we'll start with the high voltage, high current ones. And we've got 70 mics there. 77.6 to be exact. And what is this capacitor? 70 mics. Alright, so the next one, I'm reversing the polarity because it's installed with the reverse of the other one. And it is reading 79 mics, 80, 81, settling down to 80. Again, this meter is relying on sending a small residual voltage through the capacitor to arrive at that reading, and it hasn't had any voltage applied to it for 20 years. So once we bring the capacitors up to their normal operating voltage and then go test these all again, we're going to get different readings. Depending on how good the capacitor is, the readings may not vary that much. We'll find out. The next one is a 20 mics at 525 volts, and it's reading 47. These are all grounded to the same point, but I'm putting the meters directly on the negative contact of each one for the lowest path of resistance. This one's reading 55. And this one's reading 30.
Wow.
Now this is the worst in terms of leakage.
Right.
and it's the closest to its actual rating.
Isn't that interesting?
Yeah.
So the middle one's the funkiest one, right?
I think this is the funkiest looking. This one is
right in terms of.
I think you're right. The middle one was. This is 47.
And I think the middle one's 50 plus.
Yeah, 55.
55. Okay.
They're pretty close.
47,
together.
55, and 30. Interesting.
All right, so now let's go with the LCR meter and see what we get. Starting here, we were like almost dead on where it was supposed to be. 63. That's still great. A little lower, but still well within tolerance. This one, 66. Same deal. A little below the rating, but well within its tolerance. Here we've got 18.6. And again, this is a 20 mic capacitor, so that's great. This one is reading 19. Fantastic. This one is reading 21. So all the filter capacitors in here, readings wise, are well within spec, and I have no concerns about powering this up.
The measurements we're getting between these two units that's kind of.
Again, these are all in
Fascinating.
circuit, so they're wired together with other components,
Got
resistors,
it.
and so on and
Got
so
it.
forth.
Okay.
So this is doing a better job of
Just evaluating those particular pieces.
as if it was disconnected.
Right.
That one, not so much.
I see.
So that's a normal thing you expect to see. Now, when we take them out, you might see something a little different. Here is a capacitor, just happens to be laying on the bench, and it's a different type of capacitor, so it's a different example. But this is a 0.1 mic capacitor.
Okay.
0.1 mic is equivalent to 100 nanofarad, which is a different way of expressing the capacity of the capacitor. So it's effectively reading well within tolerance. 98 nanofarads is equivalent to 0.1 microfarad. Now we do it on this LCR tester. Same thing. So now you can see these are testing, get almost the identical 97. This was reading 98.
Yep.
So we're getting almost the identical reading between the two because it's not in circuit.
Exactly.
Okay. Now when I said I have no concerns about powering this up now, I meant that within the caveat that we're not going to just fire it up.
No.
We're going to bring it up slowly.
Yeah.
And we're going to watch it while we bring it up slowly. I'm not going to concern myself so much with these down here. In fact, I'm going to flip it back over because we're really concerned with the ones that are on the top. And with regard to the voltage coming in, we're going to read the voltage across the two units in series. This is ground here, I believe. Let's just verify that. Yep. Go back to the capacitor mode. Get my little, I don't have to have my fingers on it clip.
Oh yeah, we're plugging it in now. That whole thing.
Right. We're plugging it in, but again, we're not going to see big voltage yet because we're going to start out very, very low. So right now, this is our voltage monitor. This is our variac where we control the voltage going into the amp. And this is our voltmeter where we watch the power supply come up.
Okay, now a question at this point. What are we guarding against by powering it up gently?
Okay, This is called forming.
Okay.
And what we're doing is we're helping the capacitor to restore itself to its original operating condition.
Mm-hmm.
The insides have sort of separated. What's called the electrolyte inside tends to separate inside.
Yeah, that was my salad dressing analogy.
Right. So if you just apply full voltage on capacitors like this that haven't been turned on to a long time, they will generate a lot of heat trying to reform quickly.
Oh, okay.
And that will cause the ends to really blow out.
So we could theoretically see that happen if we didn't do this correctly.
Right. So we're only going to give it like increments of 10 volts every. We're going to start off really slowly. We're going to put a voltage on them about 10 volts across the two.
Okay.
Between 10 and 30 volts. We're going to read the current. Either I'm going to grab another meter to monitor the current, or I'm going to reset one of these meters to do that. So we're going to take a little break.
Okay.
I'm going to reset this so that I've got a current monitor. And then what we're going to do is we're going to turn them on, apply some power, and let it sit for a while. And what we're going to do is we're going to watch how much current is being drawn by the capacitors. Now, the capacitors really shouldn't draw any current, but they will draw a little bit of current because they're going to be in the process of reforming. And so once the electrolyte starts to restore itself to its normal stability, the current will drop down. And at that point, we turn the voltage up a little more and give it some more time to charge up and then stabilize, and then we turn the voltage up. This is called forming, and it happens on all these capacitors simultaneously. We've taken the tubes out so that there's no load on the power supply. All we're doing is bringing up the voltages across each of the capacitors so that they can reform. And also, we don't want to have the tubes in when we're slowly turning the voltage up, because we're basically starving the heaters, the filament, the filaments of the preamp tubes with those low voltages, and we don't want to risk damaging the tubes by doing that. So that's why they're out. All right, so I'm going to go find a meter to use for current monitoring, and we'll be right back.
Okay, we're back.
All right, I have my AC voltage monitor. I have now my multimeter is set to DC voltage monitoring on here, and now I have a current meter. So
awesome.
I'm measuring the current in series with the voltmeter, so we can measure current and voltage simultaneously as we bring up the voltage. Now I'm going to turn the power and the standby switch on at the same time, which is something you normally wouldn't do, but there's no tubes in here, so
right.
And there's no voltage really applied, so we can get away with that. We might see a little bit of movement, but it won't be much. Zero current, a little residual DC voltage that these two caps are seeing, because there's 3.5 AC volts going into the power supply. So as you can see, it looks like we are getting voltage through, but not enough current to read anything. So now what we're going to do is we're going to bring the voltage up very slowly, and we're going to monitor the voltage coming up, the AC volts, the DC volts, and the current meter to see if there's any changes there.
Okay. So variac.
Okay, looks like it's trying to read 1 milliamp now, and we're at 30 volts across both of the capacitors. So each capacitor has got 15 volts across it, and we've got and of course this is a solid state rectified power supply, so there's not much voltage loss between the voltage coming in and the rectified voltage going to the filter capacitors. So we're at 30 volts across these two capacitors, and barely registering maybe a milliamp, which is right where it should be. So now we can check the other three. Trying to register a milliamp and reading 30 volts there. Reading 30 volts there, 31. They're all 31, right? And the reason they're all 31 even though there's resistors in series, is because there's no load. And with no load, there is no voltage drop happening across these resistors, which are separating this capacitor and this capacitor from this one in terms of the gain stages, the tube stages that they are feeding. So there's not going to be any voltage drop across those resistors, and therefore there's not going to be any difference between the voltages at the top of these two, this one, or this one. There's also not going to be any current difference unless one was just dead shorted. And so far,
Right.
from our test, we determined that they weren't shorted. They were just not exactly at the values they were supposed to be, but according to the Lcr meter, they're actually in the ballpark. And our concern about this one bugging out a little bit isn't being borne out by what we're seeing here.
No.
So,
Or the previous.
and because there's no current being drawn here, a milliamp, that's not enough. 30 volts at a milliamp is not enough current to cause the electrolyte to overheat. So we can actually get away with running this maybe up to 50 volts. And actually, normally what I would do is I would run it up until I start to see some current draw. So let's see what we get at 50. Zip, which is good. We're reading a milliamp of leakage on each of these three capacitors and these two in series. Since they're in series, we've got 50 volts here, but since they're in series, each capacitor will have 25 volts across it. So we can check that by going to the junction of them. And there we read 25 volts. If we didn't read 25 volts there, that would mean that one capacitor is bad and one is good. Because one capacitor would carry more of the load than the other one. But we were at 53 volts and halfway, and at the halfway point we're reading 25 and a half. So again, everything is looking really good and there's no current draw. So I think that under the circumstances, we're going to go, now that we're up at 50, we've still got a milliamp there, still got a milliamp there, still got a milliamp there. So we don't have any concerns right now, and we don't have enough current being dissipated by the capacitors to indicate that the electrolyte is going to overheat. So technically we could get away with, I would feel at this point comfortable going up another 50 volts and keep turning it up until I see some activity. But the fact that we already know that it's been sitting idle for 20 odd years, I'm just going to give it the benefit of the doubt and just let it sit there and idle with 50 volts across all of them, just to be sure. And
Because it's your baby.
yeah, so we'll leave it for a half an hour. And then when we come back, we'll check it again, and we'll probably still be at all the same readings. So remember, we were at 53.2. Any variations at this point on that voltage are probably going to be caused by line voltage variations more than anything that's going on in here.
Interesting. Okay.
But we're nearby enough that we can come back and check it. There's no heat there. If I detected some temperature, I could put my temperature meter on there and we could monitor that to see if it was gradually rising or leveling off. But so far there isn't anything to measure, so no point in doing that. So we're looking good. We're going to leave this. I haven't changed the voltage. Notice the voltage has creeped up a little bit. And the current meter is now blinking 101010. That means that it's trying to decide it started out at 1 milliamp and it was pretty stable at 1 milliamp, but now it's starting to flicker up and down. The line voltage is rising up a little bit and the capacitor voltage is going up a little bit. That's what normally happens when you're forming capacitors. As they form, they become more stable. When that voltage goes up, it's because whatever residual current is going on in the capacitors while reforming is decreasing. So there's less load on the incoming voltage and it will drift up a little bit, while the current will either stay stable or go down. And as we see, it goes down to 0. It's not actually going down to 0. What it's doing is it's going from 1 to below the halfway point. Once it goes down to a half a milliamp,
There's not a...
it reads 0.
Yeah, there's
So
no
if it's
stop
on the plus
there.
side
Yeah.
of half, it's reading 1. If it's on the negative side of half, it's reading 0. So we can safely assume there that the meter resolves at 1 milliamp and we're reading less. We're reading,
It rounds up.
yeah, rounds up or rounds down. So we're probably 500 to 600 milliamps, which is great. Still no heat. We're not going to see anything really different until we get the voltage up to its working range. So we're going to take a break at this point, let it cook for half an hour, and then we'll come back and we'll start gradually, like every few minutes, start bringing it up. Or maybe we're at 50 volts. We'll go up another 50 and see how it behaves.
Okay.
And then if it's behaving okay at 100 volts, then we'll just go up in 50 volt increments until we're at the full supply voltage, which is unloaded roughly 500.
And we're back.
Right, so we're still sitting at 55 volts, give or take. So whatever little variation we were seeing is just line voltage variation. So everything is cool to the touch, which is a very good sign. So I'm just gonna go.
Give it some juice.
I'm just gonna go another 50 volts for 100, which at AC that just went to 55 volts from 35, but for DC it went to 100, which is what happens when AC is turned to DC and then put through filter caps. So here we are at 100, 101, still 1 milliamp.
Yeah.
There's no leakage. Exactly half the voltage between the two caps, which is what you see because of the voltage divider. There's two voltage divider resistors in there that guarantee that each capacitor gets approximately half of the voltage across the two series pairs. So there's 52 on that pair, and or 52 on that the top leg capacitor, and might get out there, 48 on the other one. Totally acceptable. That's just the tolerance of the resistors. There's 220k 5% resistors in there. So the tolerance of the resistors will cause that voltage division, which would be dividing by 2, to vary a little bit depending on the tolerance of the resistors. So again, we're still at 1 milliamp. There was no increase in leakage current. So, basically nothing to see here, folks. Even though this amp hasn't been turned on for 20 years, there hasn't been any significant degradation in the filter cap since the last time it was operated. And apparently an hour at 50 volts DC was enough to take care of whatever forming may have needed to happen. Again, absolutely no surprise. I don't even know if it's worth the effort to go step by step. If we were seeing something that indicated we should be proceeding more cautiously, we would have seen it by now. So, based on that, I'm going to go another 50 volts. And now we see 2 milliamps. So now we're getting up to a significant enough voltage to where we're seeing some leakage and an indication that we might want to proceed a little more cautiously. The main filter caps, the ones that are reading pretty correctly before, it's toggling between 1 and 2, so that means it's right at about 1.5 milliamps. Still nothing. When you have a capacitor that really needs to be formed, you're going to see 5 to 10 milliamps at the initial forming voltage, which in this case would be 150 volts. Now we would have seen 10, 20, 30 milliamps there, and then it would have taken a half an hour to drop down to 2 or 3 milliamps. But we're not seeing anything significant. It could very well be that what's called the working voltage of the capacitor, the maximum voltage is at which the capacitor will operate within specification, is 525 on here, or 350 on these, and potentially the working voltage would go down as the capacitor aged. But then again, if we were experiencing that, you'd start seeing it already. For example, the first 2150 power amps we made, the first 100, we had ordered capacitors from probably Sprague, the big computer grade 300 mic capacitors, 2 of them in series. And then we got a notification from the supplier that they were going to be 3 months delayed, and we were already starting the production of the amps. So I went to a local surplus place to see what they had, and they had some mid-1970s computer grade filter caps that had the same physical dimensions and the same voltage rating and capacitance rating. And when I looked closely, I saw a pretty familiar looking number sequence that was the Fender catalog number sequence. So I identified them as Fender capacitors. They had been in Fender's inventory, and that's why they had their inventory number stamped on them. And it turned out that they were the capacitors used in the Fender PS400 bass amp. So a really high quality cap, and they'd been sitting in storage in basically this building, which was always cool inside, no matter how hot it is outside. It's cool and dry. Being in Southern California, the dry climate, actually capacitors tend to last longer than they would in more humid climates. So I bought 10 of them, and I took them back to the shop and put them through the forming process, and they formed just like a textbook forming process. You could see a gradual climb in the current up to a peak, and then it would drop down to normal idle, and then you turn the voltage up 50, it would climb back up 10, 20 milliamps, drop back down again, and it was very predictable. By the time I got all done, I put them in the first 100 2150 power amps, and we shipped them, and most of those amps are still in service today and have never needed those capacitors changed. So those caps were almost 20 years old by the time we put them in those amps.
Wow.
So that would mean that they're 50 years old now.
So
the amps are 30 years old and the filter caps are 50. And whenever one comes in for servicing, which is rare, they almost never need a cap replacement.
That's funny. And I mean, that wasn't any sort of thing that you announced.
Oh, no.
New old stock capacitors.
Yeah, nobody knew anything about that.
And so after that run, was it, did you go back to the Spragues?
Yeah, they came in after that. So for our second production run, we used the new ones, and they behaved just exactly the same way. Well, we're looking really good here at 150. So let's take it up to 2. Now, normally I wouldn't skip ahead this quickly. Normally I would just every half an hour.
Yeah, you'd leave for a little while and come back.
But based on the results I'm getting here, I just increased it another 50, and now it's toggling between 2 and 3 milliamps, but it's staying on 2, which means it's 2.5 milliamps, which is nothing. I could actually grab that and not get a serious shock. But I won't.
I was gonna say, you want to put that on video?
We are good as gold. So we've got 2 milliamps of leakage current here right now of these two capacitors in series. I'm going to go to here, just measuring one of them, we're at 1 milliamp, which is, again, it's nothing. So let's go up to 250. I'm just going to keep stepping it up like this until I see a significant movement on the meter, on the amp meter. Okay, now we're at 3 milliamps and 250 volts. Oh, one thing I should point out about the line monitor voltage is it's connected to the 240 volt line. So, if it seems like we're over the voltage, we're not. We've got another 90 volts to go before we're at full voltage. We're going to go to 240 volts on that meter to get 120 volts into the amp.
That one right there.
3 milliamps. 3 milliamps. 3 milliamps. So, just by way of information, this leakage current that we're seeing, it's the combined leakage current of all 5 of these capacitors together. So if we got up to as high as 5 milliamps on any one capacitor, that means that's 1 milliamp each spread across all 5 of them.
Right.
So we're still rocking. No heat, no even perceptible warmth. $50. Still at 3 milliamps. Of course, we're not going to feel any heat, because if we were going to feel heat, we would see the current draw ramp up significantly, and the heat would just be the verification that there was current being drawn.
Okay.
So I'm just basically feeling the capacitors because I'm not believing my luck here.
You're pushing on the bruise.
Well, I mean, it's always been my contention that a simple operation like this would supersede a cap replacement for most general applications, unless you're doing hard touring and beating the shit out of the amp, cranking it all the way.
Yeah.
And every night, 3-4 hours, sound check, leaving it on after sound check before you go on stage, all that kind of stuff. Some, real road warrior usage. Then, yeah, your entire show is dependent on that, and that'd be a situation where you're not being super anal about that it's all original or that it sounds the way it's always sounded or this or that.
Yeah.
In my application, this thing isn't going anywhere, and especially not...
You're not going on the road next week, Steve?
If I do, it won't be with this. Okay, so we're at 350. And we've got 50 more volts to go because we're at 190. And we're at accumulated 4 milliamps of just combined leakage amongst all 5 capacitors. Again, nothing. We're probably starting to see a little bit of the voltage drop across the decoupling resistors play into the picture a little bit.
What are we going up to now? All the way?
I'm going all the way. I'm
Making the jump to light speed.
Well, I'm going to 238, which is 116.
Ta-da!
And then we are at 430. 450 at no load. And we got 5 milliamps of current there. 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 And there. 436. 450. So we got about a 15 volt drop across all the way down to here. From here to here, we've got a 15 volt drop across these two resistors. That would be an indication that the one on the very end probably is introducing a little current leakage that's dropping the voltage across there. But again,
Which doesn't
it's
mean
significant
too
enough.
much,
Right.
unless we plugged it in and we heard it doing something weird. But what
Or
it,
smelled it or felt it.
okay.
We're a bunch of happy little campers right at the moment. And so we're at this voltage, and I don't think sitting here for another 10 or 20 minutes is going to make any difference, because I'm not seeing, like I described earlier, we didn't see a rise that's starting to level off. We just saw a gradual residual increase in the combined residual leakage current of the capacitors themselves. So that's not anything to be concerned about. To the point where I'm ready to do this. What I'm going to do now is turn off the power, and then I'm going to discharge the filter caps using a 10K resistor.
We unplug it?
No.
No?
So what I'm doing is I'm discharging all 5 of them. I'm turning the standby switch on to do that. I'm discharging all 5 of them by discharging the end one.
Okay.
As a consequence of this one being shorted to ground through these dropping resistors, that goes all the way back to the main one and discharges all of its voltage. Let's verify that. See, we're down to 1.5 volts now. So that's all discharged. See, so I've got a 10K load across this capacitor to ground, and it's still storing a half a volt. So if it was a dead capacitor, it wouldn't be doing that. That means it's actually capacitating. Can't believe I said that out loud. So now, an indication of the last time this amp was retubed. It's got Mesa Boogie GE6 L6s, or Sylvania, sorry. So the last time this amp was turned on, like I said, was 20 years ago. But the last time it was retubed was when I worked at Valley Art, so that would have been between 79 and 83.
Wow.
And I know that because of these Amprex 6681s, which are industrials 12AX7s. They're basically computer grade 12AX7s. And they were all the rage at the time. 7980, when you could still grab them in quantities. And so now we'll be able to go in just brute turn the power on. So again, we're going to ground to system ground, and we're going to use a voltage probe off of the main filter supply and keep the current meter active. So that we can monitor that behavior. Right here. This is the main filter supply right here. Go. Zoom. One thing that we can do while we're here is check here. Check this, the bias supply capacitor. No leakage current. We've got minus 59 volts there. The other fun thing that we can do is we can actually check the ripple in millivolts. Now this is another operation where you can help yourself evaluate what's actually going on in a power supply. Taking off the little safety clip on and going with a probe. So here we have no voltage to the main supply yet because we're on standby. And there's the main supply there. So what we can do is we can go to the AC voltage mode and we can look at the ripple on the main filter caps, and here we have, there we go, 1 volt of ripple, which is typical for the main filter caps.
All right, define ripple.
When you convert AC to DC through rectifier diodes, then you send that rectified voltage to a filter cap. So you've changed a sine wave that has a positive and negative swing to a doubled sine wave that has just positive swings. So you reverse two of the swings. So
okay.
It just looks like a series of humps. That is the unfiltered DC voltage. So what you do is you basically pump those 120 hertz humps into the filter caps. And the time it takes the filter caps to charge and discharge is how much you smooth off the top of the humps in the rectification process. So normally in a solid state rectified power supply, you'll see roughly a volt, a half a volt to a volt RMS of power supply ripple, because that's where all the current is being drawn from. That's at idle. When you turn the standby switch on, which we're going to do right now, that ripple increases because the current draw increases. Let's go. Tripping. Now we have 7 volts of ripple on the power supply. This is the tube plate power supply. So we have 7 volts of ripple there. And then downstream of the main filter supply capacitors that supply the voltage to the other tubes, there's a half a volt of ripple there. And on the very input stages, there's 30 millivolts there. And between 20 and 40 there, which is, it's typical for...
Yeah, that's pretty wavy.
Well, it's It's not
Does it?
ripple. What's happening there is maybe just the noise of the preamp tubes is causing the.
But so that never just settles into a
It never
steady number.
completely settles. No,
all
there's
right.
always a little bit of noise that you pick up.
All right.
So I'm reading AC, but now I'm going to read DC. So here's the DC supply, the standby switch on, 428 volts under load, and then the very last stage down here is 385 volts. Now, a fun thing that we can do is we can actually look at the ripple in the different stages.
Oh, cool.
So here's the ripple on the main power supply here. I guess I need a ground reference for that. So
Alligator clip selection.
yeah, baby. I like data. Okay, we will ground that. So you ground it to the chassis here. And it's a very high level, so we're going to turn this way down. There we go. Okay, this is what power supply ripple looks like
All right. Oh yeah.
at the plate, at the tube plates. And here's after stage after stage after stage of filtering all the way down to the very first preamp stage. You have to really crank up the scope sensitivity to even have any hope of seeing any of it, and we won't.
Wow.
Because it's all filtered out by now.
Wow.
So
I'll be damned. The
main
filtering actually filters.
Well, yeah, the main ripple is caused by the power supply. We've checked all the voltages all down the line, and we've seen all the correct voltages for each preamp stage, from the plate supply to the driver to the individual tube stages.
And the filtering is working as it should.
One thing that we can do, because we had this one capacitor here that
It was a little
was
wonky.
wonky looking, let's look at that.
Okay.
There should be about 1 to 2 volts of DC on each of those pins. So here's the one that we tested this, and it looked pretty okay.
Right.
So there's 1.9 volts on that preamp tube cathode. That's where it should be. And we've got
Pops up to 2.5, 2.6.
not getting the voltage I want there, but that's the tremolo stage, so it could be because it's not oscillating. I'm not seeing the normal voltage drop. It's not operating like a Class A triode in that part of the circuit, so I won't see a voltage there. But we do see it there, which is where it belongs. This is this stage here.
Okay.
And then, so we should be able to pop over here and see basically the same voltage. We do. And then over here, the same voltage. So, now we get to put a signal into an input. So let's go into and what it's telling me is that we have a dirty palm.
Oh, that's cool.
Sure enough, we got a very dirty pot right there.
So we can clean that out and
Yeah.
fix that up.
I'm cleaning it out right now.
Oh, you're not even putting any junk in there.
No, I don't like to put junk in there because you know what
Okay.
happens when you put junk in there?
There's more junk in there.
Well, it actually attracts dust. So
Okay.
once you start using it, you have to continue using it.
Oh, it's like using chapstick or Carmex.
Or WD-40 or what's that stuff you put in the oil?
Man, I don't know because I don't use it.
All right. So here is what a normal amp looks like running at full power into a load.
Okay.
This is the
Yeah,
effect of the
tell me
ripple
about
in the
that.
power supply.
Uh-huh.
So that doesn't mean the filter caps are bad. That means you're at maximum output power.
So you'll see that in a brand new amp with brand new caps and everything.
That's right.
Okay.
And as you can see, this amp does not have adjustable bias. Oh, yes, it does. Look at that. I forgot.
Ta-da.
So I can crank that down if I want to.
Yeah, let's look at that.
This is where I last set it in probably 1980.
I love that.
And so this is going
Yeah, with
down.
those tubes.
Yeah.
Yeah.
So this is turning it way down to where you can see crossover distortion there.
Okay.
And then we bump it up to basically where it was. It might have been a little on the hot side. Probably there is pretty good, and we can easily check that just by doing a voltage drop across the transformer primaries. We go here. And we go here. Around, should see usually about 1.5 across the primary halves is good. Gives you about 40 odd milliamps of idle. So about 1.5 volts across the primary. There's a slight difference in the blue voltage versus the brown voltage because the number of turns in the primary are different on the halves. It's complicated, but it's slightly different, so you see a slightly different voltage drop to get a balanced with a match pair power tube to get a balanced sine wave, which is what we're getting now. So, okay, we've cranked the thing all the way up to practically square wave power in the relentless pursuit of cleaning the pots without pot cleaner. And here, not so much problem with the bass control, the speed, the intensity. Now let's turn that down so the tremolo will actually work. Oh, we have to engage the tremolo. Let's do it. We'll find a suitable ground point.
Do you have the pedal?
I do. It's in a box somewhere. Here we go. Okay. We have tremolo. One indication that our cathode filter caps are actually doing their job is that the tremolo is working. If those weren't working right, the tremolo wouldn't tremolo. So we're good at that. And real interesting that the normal pot, well, it's showing a little bit of dirtiness, but a little bit of grunge. That one, treble control is always the one that really shows it up. Those are cleaning up real nice. And I'm not going to get too anal about those. I'm not going to be moving them around enough to get anal about it. Switch is a little dirty, we'll take care of that. Alright, so now we've got a very low input voltage and we set this to, let's just set it to where the amp is at the point of clipping, right there. 4.5. Now let's set this one to 4.5 and check that. We have 7 volts AC coming out there. That's the voltage that's coming out of the speaker out. This is, like I said, we're into a fixed load. So we've got 7 volts RMS coming out of there. And we've got 10, 11 volts RMS going out there. So that means that the normal channel actually has a little bit more output.
Why would that be? I would think
because it doesn't have the tremolo in the circuit to.
Oh, I know. We were
load
talking about a super reverb. The reverb circuit is what would
the reverb circuit makes it
ramp up the tremolo.
Ramps it up. The tremolo circuit pads the signal down a little bit. So that's exactly normal. So we're not seeing anything problematic with respect to the cathode bias capacitors.
Mm-hmm.
So therefore, I'm not going to give them a second thought. Now, the last test that we can do to check for ripple or any problematic filter passes is just listen. So we have our test speaker right there.
Yeah.
With the volume on 0, there is no hum coming out of there. You'll be able to hear it. On our amplifiers, the specification for audible noise at the speaker output under a normal speaker load is 3 millivolts or less. So
that's what we're dealing with here. We're using that as a baseline.
yeah. And so here's a this is actually I think that's a 16 ohm test speaker.
That would make sense.
And we got 30 millivolts of noise. So that's what used to be acceptable noise.
Interesting.
Oh, I forgot. We have the volume. Both channels are active. So if you've got the volume up on them, they'll contribute some noise. So with both volumes down, we've got...
Okay, that brings us down to...
12. See,
wait, it's kind of moving back up.
yeah, plus because two things are happening. I'm moving this around, and this is the filament wires right here.
Oh.
So I've got my probe laying right on them.
It's almost like a wand.
Yeah. So if I do this,
Closer
it
here.
should go down. And it did go down a little bit. But
Yeah, but at one point you had it down around 12.
okay. Well, it's a 2 ohm amp, and I got it at 16 ohms. So
Okay.
it could very well be. So I've got this LCR meter here. Let's just check that out. Because it's running, it's got a fan in it. Turn it off. Yeah.
How about that?
Okay, why?
Yeah, why?
Because this tool is making noise.
Sure,
The speaker's plugged into the output.
Uh-huh.
The speaker's acting as a microphone, feeding that noise back into the output of the amp, and we're reading it right here.
I want to turn the phone around and show my mind being blown. I had no idea it was that sensitive. That's...
Yeah, just by talking, the speaker hears us, and it'll feed that into there, and we'll be able to measure it.
This is like guitar player science hour. You're kind of like Bill Nye.
Okay, that's not going to behave, so I'm going to go ahead and...
Oh, here we go.
But you'll notice that I have this bent a little bit, and it's squeezed right there. I don't want a big spray of stuff.
Oh, so you got a little added bottleneck that you introduced in there.
Right, and not only that, but I'm not going to push this button down really hard. I'm just going to barely tap on it. I only want a drop or two of...
I'm never able to do this without it just exploding everywhere.
You probably didn't hear that. I jiggled the top back and forth a little bit so I could get it to go down slowly.
You're not pressing. You're moving it like side to side.
And it just... did you hear it make a little...
I did.
That's... That.
Okay.
That's all it needs.
I've been doing things very differently.
Well, see, that's the problem with the contact cleaner is if you use too much, it will attract dust. And that will make them noisier. So just that little tiny...
And look, guys, it worked. Remember just a moment ago it was scratchy.
That one's okay.
And that one took care of itself.
That one was already good. That was good. Okay. So now going back to the...
What is this contraption you're picking up here? What do we call this?
It's called an electrified guitar.
A 6-string twanger?
5.
A 5. Is that my fault? Did I break that one?
You might have. I've always felt
like months ago.
the 6th string was optional. Ask
Keith.
So, the last thing that we're going to do to check to make sure that we're all in
Let's play some rock and roll.
shape here is, remember we had this sort of goo coming out of this one and couldn't verify.
Yeah, and we'll recap. Pun intended.
So
let me see if we can.
So we're gonna go
that black goo around there. Okay.
So I'm gonna go 3, 6, and 5 on both channels. Only on this one I'm gonna go 3.5 because of that slight attenuation by the tremolo.
6, 6, 6.
We'll get there.
All right,
Okay,
take
now.
27.
So we have a very similar tonal balance between the two, which means if this capacitor was 20 times more capacitance than this one, as the meter showed, this channel should
It'd be
bassier than
super
this one.
dull, right?
Okay, 666 per channel.
You know, at that volume, the speaker says, "Hello, what's up?" You can hear it.
Now, it's going to be artificially dirty because it's a 16 ohm speaker and the amp is 2 ohms.
Right.
So it's going to be breaking up quite a bit too soon. And that's pretty much what we needed to see from there. There's one more quick thing that we can look at
Okay.
before I go to the next step, which is going to be, now the capacitors are all charged and operational and have had voltage on them for a while, we'll go back and test the capacitance of each one again.
Okay.
Before I do that, I'm gonna run a sine wave signal, or square wave signal this time, into the amp. And I'm gonna do that at the input of the phase inverter to get away from the tone controls. We'll go square here.
All right. I want to see how you actually achieve this.
Yeah, me too. Because I'm losing track of what I'm doing. Hello. This tells me the signal going to the unit. This is going to be our ground.
All right. How the hell are you doing this?
Ground signal. I have
So
I
where
have the
is
main
the
speaker.
test?
I have the main speaker output going to the load.
Okay.
So it's set for 2 ohms.
Okay. Where's the square wave coming from?
The square wave is coming from the signal generator here, and that's this. And I'm going to feed that directly into the phase inverter, which is right here. This is where the two channels mix together, and this is the phase inverter coupling capacitor.
Got it.
So we're going to go in there to get around the tone controls. So right here, you have a nice, and of course, this signal is independent of all the controls here because we're past all of that.
Right.
So, look at that. That is the output stage square wave, which is pretty square, and that means that the output stage of this amp is pretty linear. Now, when you're plugged into a power station and you're tweaking the reactive load, this is what's happening on the low end. You're bumping up the lows, which
Okay.
is...
You know what? I'm gonna get up close here, and then you tell me what you're doing on the power station.
Okay, on the power station now, both switches are set to flat.
Got it.
Okay, now the bottom switch goes to warm
Uh huh.
and then to deep.
Wow.
So you can see when it goes to warm, the very lowest end of the square wave goes up, and then when I go to deep, it introduces a little hump and changes the shape a little bit. That means that not only the intensity, the amplitude of the low frequency bump is increasing, but it's also shifting in frequency, shifting down a little bit.
I see.
Which is what a speaker that has more resonance would do.
Well,
Like say comparing a speaker with a 75 hertz resonance to a speaker that has a 50 hertz resonance. So,
and your nomenclature there, the way you named it, makes sense.
right.
Right.
Okay, so we're back to both flat. Now we're going to switch the top one to bright, which
Look at that.
which bumps up the high frequency.
Yep.
This is the high frequency, and you see a nice long slope there. Now, for edge, which some speakers, as you play up the neck, the speaker has a real pronounced detail or brightness as you play up the neck.
Or screechy.
Right. That would be indicated by this.
Oh, look at that.
You see a distinct.
Now, what is this going on at the very end? The very edge?
Well, that's
Because that's
called.
not there with bright.
Well, it's there. It's just not as obvious. You see this
It's
little
inverted, though.
teeny little peak.
Yeah, but that's a peak. Now when
Right.
you... Well, maybe...
See, it isn't moving. It's just that the in a bright mode, the frequency shift caused by the reactive load is overtaking that little
Okay.
anomaly there, and that anomaly is called ringing. That's the transformer oscillating at a very high frequency at a very small amount. That's kind of one of the things that when an amplifier has negative feedback, it's to control things like that. If I disconnected the negative feedback meter, you'd see that ringing shoot way up.
Okay. All
And
right.
that can make an amp sound harsh and fizzy. It also sort of increases the overall gain of the amp, so
Exactly.
it could be mid-rangey and more distorted, and it will mask that fizz. But
You almost think you're browning the amp out a little
yeah,
bit and
yeah.
rolling
But
stuff
if you play that same amp quietly rather than dime it, it'll be fizzy.
You're going,
When you turn it down, you won't like it. It won't start sounding tolerable until you turn it up and get past that fizz. Where the
But we're also not addressing what happens to the low end when you do that either, which
That's
is not
correct.
It's a pretty nasty
That's
thing
correct.
on a Fender.
So now we're going to do the last step, which is turn everything off. And we're going to see. I turned the power up, but I left the standby on so it'll drain
Sure.
the voltage in the power supply faster. Because now what we're going to do is we're going to measure the capacitance again. And I'm doing it from the other side of the amp as opposed to the top where the power supply is. Well, you know what? Let's do it this way. Let's look at this one. This was the worst offender of all of them.
Yeah.
Let's see what it has to say now. Okay, it's still saying 213 mic there and 238 mics there, which is 10 times what it's supposed to be.
Settled into 232.
Let's see what the Lcr meter says. Yeah, see, it says it's 100 mics on that one. And 95 on that one. So it's over here.
This is going next door. Same cap. Different location on the circuit.
Yeah, this is the one that was reading correctly previously,
Right.
and it's still reading correctly.
Yeah, look at that.
Again, this is a 25 mic cap, 16 mics is fine there. Let's try here. Yeah, good. So technically, this capacitor is bad. But it's not bad in a way that it's really affecting the tone that bothers me, that's going to drive me to remove it and replace it right at the moment. I'm going to leave it because I don't use this channel that much and it isn't hurting the effect. If you heard
Yeah.
when we dimed it.
Yeah.
At 100 mics, it actually should be increasing the low frequency response a little bit. So that's not a normal reading for a cap like that. It's just practically reading like it's an open capacitor. So that the bias resistor on each half of that capacitor must be influencing the behavior a little bit. That said, I was perfectly happy with the way it sounded, and I don't feel inclined to change it. And like, I'm not going anywhere, and if it does fail, the worst that can happen, it'll be noticeable. It's not going to break anything else. The bias cap didn't change after the reforming process. Now let's see if anybody else didn't change after the reforming process. Now previously on the main filter caps we were pretty much right at between 65 and 70 mics on these 70 mic capacitors.
Yep.
So here we have right where we were before, about 65 on that one. And $67.5, $68, which is where we were before on that one. Now going over here, all of these were reading right around in the range of 20.
Yeah, the one in the middle was
19.
a little higher.
19.5.
Oh, interesting.
They kind of settled all into more of a similar range than before.
I think I'm also thinking of the reading on the other.
Maybe, but this
Scale.
one was the closest to exactly, and this one is 21.1, 21.2. So, all right, we're not changing the caps.
Say it again.
We're not changing the capacitors. We are not recapping this amp. There's no logical reason at this point to do that.